Have you ever paid for something online? Maybe you paid for your textbooks this semester through the AC online bookstore, or maybe you even paid your tuition online this semester. That process involves something called cryptography. In section 5.1.6, we will look at an application of inverse functions to cryptography. In example 7, we're going to begin by converting the alphabet to a set of numbers. This is called an alphanumeric code. So we're going to take the first letter of the alphabet and assume that it represents the number 1. The second letter of the alphabet, B, represents the number 2. So on and so forth, all the way to the last letter of the alphabet, Z, which represents 26. Then we're going to use the function f of x equals x cubed plus 1 to encode the message math is fun. Anytime you enter your personal information, specifically financial information, on the web and that information is sent to some sort of receiver, first that information must be encrypted or encoded in order to prevent those out there who would like to use your bank account or take your identity from theft. That information is encrypted or encoded and sent to the receiver, where it is then decrypted or decoded. This example will show us a very fundamental example, an oversimplified example of how that process works. So we're going to encode the message math is fun using our basic table, our basic conversion of the alphanumeric code here. So we're going to take our message, math is fun. I'm going to write it vertically. And the first step is to convert it into a numerical message. So we're going to use our table. We're going to look up each letter on the table and identify the corresponding values. T is 20. H is 8. I is 9. Some languages, by the way, do this naturally. Maybe you're familiar with Roman numerals. Roman numerals uses letters to represent numbers. Both the Greek and Hebrew alphabets not only have letters to their alphabet, but each letter corresponds to a number as well. So it's kind of interesting, FYI. Okay, so we've taken our message and we've converted it into a numerical code. Now we're going to encrypt this message using our encryption function, f of x equals x cubed plus 1. So we're going to take each number and plug it into this encryption function. So we need to evaluate 13 cubed plus 1. Let's go ahead and evaluate that with our calculator. 13 cubed plus 1. We end up with 2198. So we're going to take each of these numbers, plug them into our encryption function, and that's going to be the encoded message that we send. Now, let me show you a shortcut for this. This can get a little bit tedious, but if you'll go to y equals and type in our encryption function, y equals x cubed plus 1, then we can have the calculator evaluate all of these function values. Here's how. We're going to go to our variables key, VARS, and we're going to choose y variables. Option number 1 is function, so I'm going to press enter. And I named my function y1. So this y1 on my home screen acts like the f in f of x. So I'm going to plug in the next argument, which is 20. And so the calculator is going to take 20, plug it into the function, and then show us the output. So f of 20 is 8001. We can do this for all of our numbers. Doing it this way will really save us some time and tedium. Whoops, and down here is supposed to be 14. Okay, so next we can find f of 8. So again, we press our variables key, y variables, function is highlighted, so I press enter. y1 is highlighted, so I press enter, and then we put our argument 8 in parentheses. And our output is 513. Now, we can even make it shorter. Now that we have our function programmed in, we've got y1 on our home screen, I'm going to do second entry to recall what I just typed in, and then I'm going to use my arrow keys and just edit the argument. So y1 of 9 becomes 730. And we continue this process, again, second entry for all of our input numbers. Make that a 19 there. And our output is 6860. Okay, we can do that for all of the rest of the numbers. I'm going to pause and do that very quickly. See, that was pretty quick, right? All right, so now we're taking our original message. We have converted it into numbers, and now we have this encrypted message. So if this encrypted message were intercepted, it would be harder to decipher the original message. It would take some effort and some intelligence to decode what that message is. So that is the message that is sent and received. And on the receiver side of things, they have to be able to decrypt or decode the message. To decode the message, we would need the inverse function. The inverse function, if we did the switch and solve technique, would be the cube root of x minus 1. Again, you can verify that. So each entry then that is received is going to be plugged in to this decoding message, and we would end up with, let me remind you how to find the cube root on your calculator. That's under your math menu, option number 4. The cube root of 2198 gets us back to 13. Oh, that should be 2198 minus 1. Let's correct that really quickly. It should come out exactly. So back to my math menu. Math, option number 3. Let's call that 2198 minus 1, or 2197. There we go, exactly 13, which was my original value over here. Then we can convert that back to the letter. So this is going to be applied to each input. Cube root of 1 here would give us 1. So on and so forth all the way to the end. And our result would look something like this. The next step then, the last step, is to rewrite this in terms of our message of letters. So we're going to take 13, we identify that from the table, and we convert it back to letter M. We take number 1 and convert it back to letter A. This continues through the entire message here, and we get the original message. So step 1, we convert the letters to numbers. We use an encryption function to make it a secret code. That's the information that would be sent. Then we have a decryption function to decode it back to a numerical message, and then finally convert that into a string of characters. Now, this process, again, is oversimplified. The actual encryption may have a much more complicated function than this simple cubic function, and there may be multiple functions that are applied to encrypt the message. So you may have 2, 3, or 4 levels of encryption, which means 2, 3, or 4 levels of decoding on the other side. But at least it gives you some idea of how your information is encrypted and kept safe from theft with online purchases. Hope you found that interesting. Think about this the next time you purchase something online.